Okay, let's dive into this. Welcome back, everyone, to today's explainer. I am absolutely thrilled to guide you through this material today because, honestly, we are looking at a concept that fundamentally shifts how we view the entire universe, right down to the technology that you and I use every single day. We are talking about emergence across the sciences, going all the way from fundamental physics to artificial general intelligence, or AGI. So, to get us started, I want you to think about a question. What do a snowflake, the stock market, and ChatGPT actually have in common? On the surface, absolutely nothing, right? I mean, one is literally frozen water, one is a global economic network, and the other is an AI. But they all share this profound central mystery. You see, they are all systems where completely mindless individual parts somehow come together to create these incredibly complex, seemingly intelligent wholes. A single water molecule doesn't know it's making a beautiful six-sided crystal. A day trader isn't consciously designing the global economy. And a single line of code, it doesn't actually understand language. And yet when you put them all together, they do. But how? Well, here's our roadmap for today's explainer to figure that out. We're going to start with the mystery of emergence, break down weak, strong, and radical emergence, and then explore order from chaos. After that, we'll look at biology and evolutionary leaps, AI and phase transitions, and finally, the road to AGI.
All right, Section 1, the mystery of emergence, defining the concept.
According to a massive 2025 interdisciplinary review by McKinsey, emergence happens when interacting components develop novel properties that are completely absent in the individual parts themselves. And right at the core of this whole idea is what's called the mesoscopic scale. You can think of this as the Goldilocks zone of science. It is that scale right in the middle. It's large enough that collective behavior can actually happen, but it's small enough that you can still clearly identify the individual parts. So we're not talking about the level of a single atom, but we're also not talking about the scale of the entire cosmos. Emergence always seems to happen right here in the middle, at that mesoscopic scale, where these parts interact to form a totally new whole. Moving right along to Section 2, weak, strong, and radical. These are the levels of emergence. To really wrap our heads around these levels, we look at a foundational map created by the philosopher David Chalmers. And the absolutely crucial point here is understanding the difference between weak and strong emergence. So weak emergence means that a higher level phenomenon is unexpected, sure, but if you had enough computing power, you could theoretically deduce it just by looking at the lower level parts. Think of a hurricane, right? It's incredibly powerful, but at the end of the day, it's just wind and temperature. It's complex, but it's totally deducible. Now, strong emergence, that is a totally different beast. Strong emergence claims that entirely new fundamental laws or causal powers appear that simply cannot be deduced from the lower levels, even in principle. The parts combine, and boom, the universe literally has new rules. This specific distinction right here is pretty much the battleground for everything else we're going to talk about.
Which brings us to Section 3, order from chaos, looking at physics and economics.
Back in 1972, the Nobel laureate Philip Anderson wrote this famous paper called More is Different. And it completely challenged the idea that if you just understand fundamental particles, well, then you understand the whole universe. He pointed out phenomena like superconductivity. That's where electrical resistance drops to exactly zero at super low temperatures. The crazy thing is, you literally cannot find superconductivity by studying a single electron. It just doesn't exist at that level. It is a strictly collective behavior. As Anderson beautifully put it, the behavior of large and complex aggregates of elementary particles is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear. Basically, more isn't just more is fundamentally different. And you know, we see this exact same more is different principle when we look at human societies, too. Take F.A. Hayek's concept of spontaneous order. It tells us that vast economic order arises from human action, but not human design. Just think about it for a second. Water molecules naturally lower their energy state to perfectly freeze into ice. A flock of thousands of starlings can instantly turn in the sky together without any leader telling them to do so, which is honestly amazing when you consider that a few dozen humans can barely coordinate a morning commute without causing a massive traffic jam. Yet, human beings, just by individually going out and buying and selling what they need, spontaneously create this massive, globally coordinated economy without any central planner dictating the prices. It is a massive, mathematically complex order arising completely from chaos.
Okay, let's jump to Section 4, Biology and Evolutionary Leaps, covering the major transitions.
When we look at John Maynard Smith and Eor Sathmari's major evolutionary transitions, a really distinct pattern starts to emerge. In step 1, you have independent replicating molecules. Then, step 2, they merge to form chromosomes. Step 3, those merge to form single-celled organisms. In step 4, they merge into multicellular organisms, just like us. So evolution isn't just about small, gradual mutations over time. The really major leaps happen when previously independent parts completely lose their ability to reproduce on their own, and they merge to become a brand new emergent whole. Literally, the base unit of life itself scales up.
And that brings us to this absolutely brilliant concept from the theoretical biologist Stuart Kauffman. It's called the adjacent possible. I want you to imagine you are standing in a room with 4 doors. You open one door and you walk into a new room. But simply by entering that new room, a dozen brand new doors suddenly appear that you couldn't access or even see from the first room. That is the adjacent possible. Every single time biology evolves a new trait or humanity invents a new piece of technology, it doesn't just fill a pre-existing niche. It actually creates entirely new possibilities that literally did not exist prior to its evolution. It's like the universe is actively writing its own future in real time.
Now for Section 5, AI and phase transitions, focusing on emergence in large language models.
Right now, there is massive friction in the scientific community regarding artificial intelligence. On one side, you have researchers like Wee and his colleagues who argue that emergent abilities in large language models are completely real. They say that as these models scale up, they suddenly develop abilities, like multi-step reasoning, that the smaller models just completely lack. But on the flip side, researchers like Schaefer and his colleagues argue it's actually just a mirage. They suggest these sudden leaps are merely an artifact of how we actually design our evaluation metrics. Basically, if you use a pass or fail grade, it looks like a sudden jump. But if you measure partial progress, the curve is actually incredibly smooth. Now, as an explainer of the science, I'm definitely not here to pick a side. But I do want to show you that this exact debate asking, is it a real qualitative leap or just a quantitative illusion, is essentially the modern version of that weak versus strong emergence debate we talked about earlier.
And the data gets even more intriguing when we look at recent 2024 studies by Nikaishi, Arnold, and their teams. They impartially measured LLMs and found that these AI models might actually be exhibiting critical phase transitions that are mathematically analogous to natural physical systems. Just like water transitioning to ice at a very specific temperature, these massive AI models are showing structural phase transitions in their outputs as you scale them up, or as you change their sampling temperature. They are literally obeying the exact same power law mathematics that govern magnetic fields and avalanches, which is just wild to think about.
And that leads us right into Section 6, the road to AGI and its future implications.
Let's rapidly consolidate these ideas. We have got a single, unified framework that connects the study of subatomic particles all the way up to artificial minds. And across all these different disciplines, we see 3 consistent things. First, the mesoscopic scale, where parts are just numerous enough to create a new whole. Second, universal phase transitions, where quantitative scaling suddenly triggers a massive qualitative change in behavior. And third, the adjacent possible, where complex systems constantly open doors to brand new, totally unpredictable realities. But, as we know, opening new doors isn't always safe. There is this fascinating, albeit slightly terrifying 2025 finding from Affanin and colleagues that highlights what they call emergent misalignment. They found that just giving an AI a few narrow examples can actually cause broad, generalized misalignment. And the real kicker here? The larger, more advanced LLMs are actually more susceptible to this, not less. This perfectly maps back to Kauffman's idea of the adjacent possible. In biology, a new organ creates a new niche for a parasite to exploit. Well, in AI, scaling up creates new, unintended attack surfaces just as fast as it creates new capabilities. Basically, the more complex the system, the more unpredictable its emergent flaws become. Which leaves us with this final, incredibly provocative thought. As we pour billions of dollars and trillions of parameters into building AGI, what exactly are we building? Are we simply engineering a weakly emergent mirage? A very convincing calculator that just looks really smart? Or, by scaling these systems up, are we actually triggering the next strong phase transition of the universe? Opening a door in the adjacent possible that brings an entirely new level of order into existence? It's a profound question for sure, and it's one I really hope leaves you eager to keep exploring. Thanks so much for learning with me today, and I'll catch you in the next explainer.